Hey everybody, this is Mr. Munson, and we are in Unit 2, Circles. We're going to be studying circles to a great detail and great detail. We're going to look at these first two sections, Concept 1 and 2. If you look at your student learning map, you can see what the I can statements are. Those are the those I can statements are what you should be able to do, those kind of problems, by the time you're done with this video to a basic degree. In class, though, as the flipped classroom allows us, we'll go into a much deeper understanding with a little bit more challenging problems as we practice in class, where you have me as an expert and as other students are also experts to kind of help move you along if you're having trouble. Let's go ahead and continue. So you should have gotten this student learning map. Again, here's the I can statements. Pull yours out. Make sure that you have an understanding of where we're going. Let's again continue. All right, now before you start taking notes, I want to take you through some ideas. So just carefully watch. You will be writing something down here in a second, but I want you to see if you can just kind of follow along with me. Here's two segments, a green one and a blue one. They cross each other. When they cross each other, they intersect at this point right here. And what it does is it creates two blue segments and two green segments. Now we know from Unit 1 that we can add them together to get the longer segment and so on. Now, what I want you to know is in these two particular segments, they have a relationship to each other. We could write an equation about them. So if you look over here on the right-hand side, you'll see that relationship. I just happen to say is true about this. Now, it's not always true. I'm just saying in this particular case right now, the blue pieces multiplied times each other equals the green pieces multiplied times each other. Okay, so what I want you to do is put me on pause just for a second and someplace on a scrap piece of paper or in your notebook as you get ready to start taking notes, I want you to write an equation that represents the words that are over there on the right side. Put me on pause. Now I'm hoping that you wrote an equation like this. I use parentheses to represent the multiplication. Things like this, 4x minus 1, are called quantities. And so since it's a couple of different items that have some type of operation between them, here we have 4x minus 1, I put parentheses around it, kind of keep it as a content, you know, like a package, so it doesn't get mixed up with anything. So I have 4x minus 1 times 3, and 15 times 3x plus 2. And according to the words over here on the right-hand side, that's what the equation should be. Now I'm hoping that we've talked about enough times. Do you think that's going to change their relationship if I draw a circle around them? Hopefully not. And so this is the kind of problem we're going to be dealing with today. We're going to be looking at problems where there are segments that meet inside of a circle like this, but it's just a relationship, an equation that we can write. All right, now take a look at this one. Again, I speak over here to the right, and I say, hey, there's this relationship between these pieces. One piece of the green times the whole length of the green should equal one piece of the blue times the whole length of the blue. Now, the pieces that I'm talking about at the very beginning, let's say they are the outside piece. When I say it's the outside piece, I'm talking about that piece there. So down here, let's parallel it and make it the same. So we're talking about that. See if you can just put me on pause for a second and write that a little bit more challenging equation, but see if you can do it. So the outside piece of the green times the whole length of the green is equal to the outside piece of the blue times the whole thing of the blue. Now remember, in Unit 1, we talked about adding segments together to get longer segments. I don't need you to solve anything. I just need you to write it. Go ahead. And hopefully you wrote an equation that looks like that. Put me on pause and just verify that you understand where that came from before we move on. This is the 5-foot section of the pool. We're getting ready to move to the 12-foot section. I don't want anyone drowning. All right, let's move on. All right, just a real quick review of some vocabulary words. Semicircle. Semicircle is half of a circle. We talk about semicircle being 180 degrees. If you look down at the bottom, the black there, it says the measure of arc ABC is equal to 180 degrees, so we'd write it like that. Very similar to the measure of an angle, but in this case, it's an arc. And then we always use 3 letters to represent a semicircle. Okay? And what that does is it prevents you from thinking about this side of the circle when I don't mean it. Okay? Next up is a minor arc. That's an arc whose measure is less than 180 degrees. We would write like an example, the measure of arc AB is equal to 38. We always use two letters when we're talking about a minor arc. So if I see two letters with an arc above it, I know that you're talking about the minor arc and not maybe the major arc that's on the back side. Of course, you should be using three letters to designate that thing. That's a major arc, which leads us to the next idea. The major arc is an arc that whose measure is greater than 180 degrees, greater than a semicircle. And so an example of writing that would be like the measure of arc ABC equals 210 degrees. And again, we use three letters to represent that so that the person clearly knows where on the circle we're talking about. Now, I apologize. We jumped right into taking notes, and I forgot to mention some things. I want to remind you, you should have a summary right before this. Don't forget to put today's date, whatever date you're doing it. And I've been asking you to bring in your notebooks. At some point, I'm going to open them up. We're going to look at it. I'm going to give you a grade based on your notes. And then we'll just talk through how you can make that a better grade. If there's any thing that I feel like that you could do better, then I'll let you know, and we'll see if we can update that. All right, here we go. Now again, just remember that I should be seeing a question mark in this black line. This gives you a place to write questions. It doesn't have to be a big chunk of your paper's property. It just needs to have a space there so you can write any questions you have. So in this figure, I have some vocabulary words that we're talking about here. We have a chord, a secant, tangent, and a diameter. And again, we've already gone through those vocabulary words. I have it color coded. I encourage you to get some color pencils so that you can make your notes color coded. Otherwise, it's kind of hard to see which one you're talking about. All right, let's move on to next ideas. Let's just briefly talk about two congruent circles. Two congruent circles are two circles that have the same radius. Now, oops, I've erased a piece of my thing here. So here is two circles, and each one of them have their own radius. But what I want to show you is this. If I rotate the radius for the X, black one and the green one, if I just rotate them around, I see that the black radius for the left-hand circle reaches from the center of the left circle all the way over to the center of the right circle. So hopefully now you can see better. The left-hand circle is red, and the radius goes from the black center of the red circle all the way over to the red circle's edge, which happens to meet at the same place as the center of the other circle. So the black radius coming this direction comes this direction and meets on the blue. So the two radii are identical and the same measure. When that happens, we know that two circles are congruent. Now, they don't have to overlap like this. One could be over on the left-hand side 5 feet away. It doesn't matter. If they have the same radii, same measurement of the radii, then they will be equal and congruent to each other. Two concentric circles have the same center point. Now, I want you to put me on pause, pull out your vocabulary words, find a blank rectangle on your vocabulary words. Any one of them will work. And I want you to write in concentric circles, same center point, draw this circle so that you have it for a vocabulary word. Go ahead and put me on pause and do that. All right, you might need to put me on pause while you draw that figure in. All right, looking at this picture, I want to start with characteristics of a radius and a tangent. So just remember, there's lots of different radii in this. I have P to R, I have P to N, I have P to M. Those are all radii, okay? And so some of the characteristics of when a radius and a tangent meet, such as up in this area, we find that the two meet, the radius and the tangent, meet in such a way that they are perpendicular. Okay? Hopefully you remember that from way back in the day. Perpendicular is basically they meet at a right angle. The blue statement right there, they are, and then it's like an upside down T, is the kind of the symbolic way, the symbol way of saying they are perpendicular. So whenever you see that upside down T, that means that two things are meeting and forming a right angle. All right, what I'd like you to do is just put me on pause and see if you could look at this drawing and write down in proper notation a radius, a chord, a diameter, a tangent, secant, and center. Pull out your vocabulary words, look those things through, and see if you can come up with them. Put me on pause and come back and check your work. There's an example of radius. As I said earlier, there's several different choices. Then we have a chord. RQ is a good choice. RN is a chord. It's a special kind of chord we'll call a diameter. Tangent. Tangent is a line that meets a segment or meets a circle in one and only one place. SM, ST, those are good ways of writing the notation of that particular line. Either one of those works. Secant, SQ works, but I'm going to put a line above it. Secant can be a ray, a segment, or a line, but usually when we're using the word secant, we're talking a line. If we're talking about something that meets a segment or a circle in two places, but it's more of like a segment, that's a chord. Remember, a chord is a segment that touches the circle in two different places. The center, we would just simply write a dot with a P in it because it's a circle, and that's the center of the circle, so we call that the center of the circle, point P. That's the end of 2.1. Draw a line, write the word summary, go back and just write a real quick summary. Look at your I can statements that might help you write a summary, and then come back and check for the next section. All right, the next section is 2.2, segments with a vertex inside or outside a circle. This is an example of a circle that has two chords that meet on the inside at a vertex that's inside the circle. It cuts when the two segments meet like this, it takes each one of the segments and breaks it up into two smaller partners. So like the A and the B, both green, are partners, and the C and the D are partners. Now what we find out is those numbers, whatever those links are, be it 15, 18, whatever the links are, 5x minus 2, whatever, there's a relationship between these four pieces. And this relationship is expressed in the equation that's down below. If I take one piece and multiply it times its partner, it equals the other piece times its partner. I just like to say a partner times a partner equals a partner times a partner. So let's look at an example. All right, so I have a circle. I notice that the vertex of the two chords meet on the inside. We're going to be looking at ones where they meet on the outside. That's why I'm reflecting on that. So what I would do is, if I was you, is I would definitely write underneath there vertex inside the circle. That clarifies what kind of problem it is and helps you understand it's the equation partner times partner equals a partner times a partner. So I take those pieces and I just write a partner times its partner equals a partner times its partner. In this particular equation, I have an M, and so I just simply solve that for that M to find that missing piece. Now I'm doing this with colors. You're going to have to be able to look at these drawings where it's all black and white and determine who's a partner, and it's just simply the two pieces that lie on the same segment. Remember, shorter segments can add together to give you longer segments, but we're not adding these pieces, we're just multiplying those pieces. All right, I'm just going to slide that over to the left, and then I'm going to expose a try-it problem. Why don't you go ahead and give that one a shot? See if you can just write the equation. Don't worry about solving for x, just write the equation, come back and check. If you didn't write, it was a vertex inside the vertex inside the shape. If you didn't write that vertex inside, go ahead and do that real quick, but hopefully you have in green, or your equations like mine in green, partner times partner equals a partner times partner. So now we're looking at a different kind of problem. These are segments. Again, we're dealing with segments. And the vertex is outside the circle, okay? Since it's outside the circle, it's a completely different equation. Now, I don't want you to focus on the letters and try to memorize the letters. It's more the idea of what's going on. If you look at the B, it's on the outside of the shape. And if you look at the D, it's on the outside of the shape. And then when you look at the A and the B, that represents the entire line. So D on the other side, you have D and the entire line inside parentheses. So no matter what the letters are, even if it's 15 or 18, whatever the numbers are, or it's 5x minus 2 or whatever, the idea is this. The outside piece times the whole piece is equal to the outside times the whole piece. Okay, it's the same thing. So once you have it memorized for one side, the other side is just a duplicate doing with another segment. All right, so let's go ahead and look at a problem like this and see how we'd set it up. The first thing I would do is I'd write this outside times the whole equals outside times the whole. That's a quick way of doing it. Then I would just simply take the pieces and put them in their place. The outside is 14 for one of them, and the whole is 14 plus the 3x plus 5. That's equal to the outside on the other piece times the whole thing, 2x plus 17, okay? So I'm looking at each little segment as being a way of putting the pieces together. So now if you're confused, you should put me on pause and go back and look at that drawing. Put it on pause and just look at how my equation's formed, how this equation right here is just following this template, outside times whole equals out times whole. I'm adding the pieces together that represent each little smaller segments to get the whole thing. Okay, let's take a look at a try it problem and see if you can write an equation to solve for this problem. Put me on pause, write your equation. So there's the problem, okay? Now, we'll look at solving this kind of problem later on at another time. Let's continue on. Now here's another example of a problem where the vertex is outside. So this is again an outside times the whole thing. It's got an interesting twist to it. Now I definitely know it's an outside times the whole thing kind of thing. So outside times the whole thing equals the outside times the whole thing. The interesting part is this one, this piece over here doesn't have two pieces. It only has the outside piece. So look at how I handle that. First, I have on the other one, 6 on the outside equals the whole thing, 7.5 plus 6. Then I go equals the outside, which is x, times the whole thing. And it is x. It's already given x. This is an easier problem. So then I would just simply take that x and square it, make it x squared. Let's start working the left side, combining the 7.5 with the 6 to get 13.5. So then I end up with x squared equals 81. And of course, at this point, you know, we have to take the square root of both sides, and x would equal 9. All right, now it's time for you to try it. Go ahead and draw this picture in, write an equation, see if you can solve it. Did you get the equation I did? I hope so. Let's continue going. I ended up with 192 equals z squared. Took the square root of both sides, and I got z is approximately equal to 13.9. And there you have it. Let me zoom in so you can see the problems that you're going to be doing, and good luck. Excellent. You've done a great job going so long.